chem again this morning. Is it working? Yep. Primary combustion zone. It was in the book. Okay. I can write it here. Primary. And then we've got this big area in the middle, this huge area in the middle, right? They call that the secondary is going to be the most outer one. This one's the secondary. Okay. So that one you really can't see and identify too well. Yeah, if we made it really dark, you could see it, but you can kind of see it. I don't know if we can make it any darker, but you have to come up really close to see it. It's pretty easy to see the primary combustion zone, but this whole big area in the center is called the, starts with an I, interzonal region. So those are the three regions of the flame. And here's a temperature profile of it. So, Kevin, it looks like in what region is the maximum temperature located in the flame? Right, if you kind of correlate this temperature diagram with what we drew up here, it looks like, yeah, interzonal region. Right.
So, on that diagram then, I'm assuming that primary combustion zone is that dip in the middle?
Here's a primary combustion zone, yep.
So is it saying that it's truly at about 0?
No.
Because there's no...
Look, there's...
That's just the centimeters.
So this is your temperature, but it goes 1700, 1800, 1830. It's still freaking hot in there, right? It's 1,000 degrees.
Oh, I was talking more inside where it says the burn.
Oh, okay. What is this? This is the distance. The distance you're going out in this direction, then the distance that you're going up the flame, right? So here's the height of the flame. Here's the width of it. So their flame is roughly, what, 3 centimeters wide. I think the flame in our AA is like 4 or 5 centimeters. Okay. In what region is most spectroscopy performed? Oh, what would you guess?
I guess
Yeah, you're right. It's the interzonal. It's the interzonal region, but why? For most cases, it's because that's where the most atoms are. And a lot of this period we're going to talk about today this is called atomic absorption spectroscopy. So the only thing that can be doing the absorbing are these free atoms in the flame. They can't be, for example, calcium atoms. It can't be calcium +2. It can't be calcium oxide. It has to be free calcium atoms. Can't be dimers, can't be any of this. It has to be free calcium atoms to do atomic absorbance spectroscopy. Because anything else is going to have a different absorbance spectrum. It won't absorb where we expect it to. Okay, so that's pretty much where the most atoms are. Okay.
So when you're saying the most atoms, you're talking about for your sample?
Well, all right, it pretty much comes down to this for me. What's doing the absorbing? The atoms are. Okay, now B is just what? So this is absorbance, right? B is so there's 3 ways to make this absorbance really high. We want the highest absorbance possible, right? So we can have the best signal. What was the little b? I don't know if this is much of a hint. It's the path length. The path length, right? So how the light's passing through your sample, what's the distance that the light, how much opportunity are you giving your sample to absorb here, right? The longer the path length, the better, right? The wider the cuvette, yeah, look at it, has to pass through much more sample than a really narrow cuvette. So path length is B. What was this little epsilon thing? I'll give you a hint. It has a little, it should. It's the only one that has a little subscript on it. Because absorbance is at a particular wavelength, and so is this little coefficient. They call it the molar extinction coefficient. That's not much of a hint. But something in this equation has to be varying with wavelength. Otherwise, this sample would absorb everywhere, right? So that molar extinction coefficient is just the ability for that compound to absorb at that wavelength. So the bigger it is, it's going to absorb even better. So that's what a molar extinction coefficient is. So our last one, C. C is concentration. So we were talking about what region is most spectroscopy performed. My answer was just, because that's where most of the atoms are. Why? Because I can't affect the molar extinction coefficient. I mean, that's calcium absorbed with calcium absorbed. That's these metals, you can't mess with that. The path length, well, you can't really mess with that either. I mean, you kind of can. I mean, it might be the flame looks pretty dang, well, it's kind of narrower at the bottom, but the path length isn't really going to change too much, right? The only thing I can really mess with is concentration. So I'm picking the interzonal region because I'm getting the highest absorbance signals. The reason is because that's where my concentration is the highest. And what am I studying? Free atoms, so it has to be, that's where I have the most atoms. Okay.
In the atomic absorber, the flame is shaped the way it is, that they make a long bar because it shoots this way, right?
Okay, good. Why do they make that? That's a good point. Why do they make that? Do you see what he's saying? Why do they make this long bar in the AA? Because you're exactly right. Because why?
It increases the path.
Increases the path length.
Because the laser light.
The light,
yeah. Is going to go from left to right.
Yeah, exactly. That's the only reason why they flatten that thing out, is to increase the path length. But that's, so that's going to be fixed. Okay, so you can mess with the different locations in the flame. We'll be talking about, that's what's coming up next, I think, maybe. Yeah. Okay, so why not, so like Brad's saying, your path length is coming through here. Well, why not have the path length come lower or higher, or change the height in that path in the flame. So here are some examples, right? For the absorbance, it's absorbance versus height in the flame. Okay, and they just plotted it out for different metals. So are all atoms measured at the same height in a flame, Shelby, according to this plot? Can you stick with one height and not worry about it? Right? If we were having, she's right, if we're having trouble, like getting a signal, we should really be messing with the height in the flame, right? But there's so many other buttons for you guys to mess with that I didn't have you mess with that one. Okay, but you could be messing with the height that you're at in the flame. So it does matter. Which of these elements does it look like, Andrew, that you have to analyze right when it comes out of the bloody burner? Which metal should that be?
What's it, gold? Or what's AG?
AG is silver.
Silver.
Silver gives its maximum, it just keeps going up. Silver seems to get better and better and better the higher you get. Chromium. Look at chromium. He gives the highest absorbance pretty much right when he comes out. And it just gets worse. Okay, so there's things that are going on here. Look at magnesium. He gets better and then he gets worse. So I might as well just tell you. Chromium, what surrounds the flame? What's out here? Air. And what's in air? Oxygen. Oxygen pretty much is your pick on every. If you're going to make a guess on anything that's causing problems, you almost always pick oxygen. Oxygen reacts with stuff. So oxygen, call them oxides with whatever. Pick a metal, you can form an oxide. oxides of chromium form really easily. So that's why you have to get it right when it comes out of the flame, because the oxides form. Silver, heck, no problem at all. Right? Silver, you can go even higher. Until you reach the top of the flame, it gets even better. Okay. So there's some deficiencies when using flame as an atomizer. Can you think of what one of them would be? Yeah, you can run out of fuel. That's more like a limitation. But deficiency meaning it's not good. It's not good. I mean, what the heck? An elemental problem with it. It's just a fundamental problem with using the flame as the atomizer.
Not everything's atomized.
Good. Not everything's atomized. Also, but that's not a major one. But we're getting there, though. The no, that is it. He just used different words that was in my brain. Not everything's atomized. Most everything goes where? Into the waste. That tube and everything's running into waste. Right? I think, what was the number? Oh, I thought I wrote it down. It was like 0.01. I wrote it down. These numbers are escaping me. It's like 0.01% or something. Actually gets, I don't remember the fraction. Just say most of it goes down the drain. Almost all. Almost all goes to waste. Okay. The other deficiency, you pretty much have to think about that flame, and they already made it super long to increase the path length, like Brad said. But if you want it to absorb, it has to stay in the flame. But it's a bloody flame. I mean, this stuff is just, so it's not in there very long at all. You only have like 1/10 of a millisecond. 10 to the negative 4 seconds is all the time that it stays in the flame. So not only does everything go to waste, because hardly anything goes in the flame in the first place, but when it does get in the flame, man, it's hardly there at all. So its lifetime in the flame is very, very short. So if you fork out probably an additional $45,000, forget the bloody flame. Let's do the exact same instrument, where you just take the flame out and all those gases and all that explosive flashback stuff not to worry about, and let's use a graphite furnace. Can you picture what that would have to look like? Super hot.
I imagine it would just
Compartment oven thing, but it has to have what on both sides? Well, graphite just means that's what it's made out of. It has to be openings for the, not the air, the.
for the sample, for the wavelength.
Whoa. Okay, so
The light.
because you are going to take your sample and just dump it in there, seal it up, heat the crud out of it, right? Just bake the crud out of it, and everything goes into the vapor phase. Shine light through there, you'll have it. It's not going anywhere. The time that it's in there it's going to be there forever, right? So, and they've got really good at this. I mean, these things can heat up really fast. The only issue is I think the windows and stuff, they get eaten up, and you have to be changed. It costs like $20 a run or something, because you have to change the little cells. But maybe it's not that much. But I was looking into it, and we didn't have the money for that anyway. Okay. So they call it electrothermal atomization instead of using a flame, okay, to make the atoms. Because that's the whole idea. You got to make atoms if you're doing atomic absorption spectroscopy. Some light sources. Okay. What do you think, Shelby? Is a different lamp used for each metal when doing the AA? Yeah, you're right. Now, some lamps like this one, just don't. You can take a look at it. Just don't take it out, because it's a lamp. It'll break and get glass everywhere. Some lamps have multiple elements on them, like that one. That you can use sodium or potassium, okay? But it's pretty much, you're right, a different lamp is used for each single metal. Well, have you ever wondered why? Why not just get, because it's light, and the lamp is kind of, sodium's orange. So, heck, why not make a gazillion dollars by, right, having a little light bulb, has all the colors that coming off of it, and then put a what in front to select the wavelength? Monochromator. Right? Select the wavelength of sodium or whatever, right? Heck, why have all these lamps? Put all these guys out of business. There must be something wrong with this, right? Otherwise they would do it. No. Accuracy is not the problem. It's the, well, I guess maybe you can think of it actually. Think of it this way. What is an absorbance measurement? It was the negative log of P over P naught, or P naught over P, or P over P naught, one of those two. I think it's this one. But it was two measurements, right? Okay, so if you want to make a measurement, right, your first, what does the absorbance spectrum of your sodium look like, of a sodium atom? It was supposed to be extremely wide or extremely narrow? Extremely narrow, right? Extremely narrow. Okay, if you do the same thing with a monochromator, what do we call it? The what width? Slit width. These bloody things have slits. So yeah, make it as narrow as you possibly can. Fine, but you still end up with, now on a spectroscopic level, this is really still super narrow, but it's much wider than this. Now we have to distinguish between the two, because absorbance is negative log of one over the other. So you could physically just try subtracting these two intensities out, and you would end up looking like, right? No one can tell that. You can't see the change in intensity. It's not enough. Your results are going to be totally nonlinear, and it's going to be an ugly mess. So that's why if you want to see changes in intensity and actually measure absorbance, you can't use a monochromator. You have to use another sodium lamp. So then your result would be, oh, now it's a lot smaller in comparison to what it was, right? The intensity actually went down. You can't tell that intensity went down here. There's no way you can measure that. So the source with the light source, its bandwidth has to be essentially the same or narrower than your sample. Otherwise, you're not going to be able to measure those changes in intensity. Does that make sense? So this hollow cathode lamp that was passed around, it looks like this. And they have a cathode and an anode. It's filled with an inert gas. The cathode is covered with the what of interest? Probably the metal, right? Well, I said element, but the metal that we're interested in, okay? So you have to somehow get copper light out of this thing, because this is the only way it's going to work. Because copper atoms are doing the absorbing, you have to have copper light because you need the bandwidth to be the same. Otherwise, you can't measure the change in intensity. Because again, you need to measure the transmitted. You need to measure the transmitted and the incident. Otherwise, you can't make an absorbance measurement. So that's why we have to generate copper light if we're going to analyze copper atoms, because those absorbance lines are so narrow. Okay, how does this thing work? We said that the cathode has copper on it if we're trying to generate copper. Okay, we're going to have a really high potential here, E naught, between the cathode and the anode, a huge potential. the whole thing is filled with an inert gas. Inert means doesn't react. And it's pretty low pressure. Okay? None of this would work without the inert gas. Sputtering. Somehow we got to get these copper atoms that are on this cathode into the excited, off the cathode in the first place. Because if it's copper atom stuck to copper atom and emits light, that's going to be a different emission spectrum than what we want. We want copper atoms free to emit light. So not copper ions, nothing else. We want copper atoms. So they have to emit their light, then they got to deposit back onto this thing. So they can do the whole thing over again. But somehow you got to get them off. Somehow you got to get those copper atoms off of this cathode and into the gaseous state and excited and have energy to emit light. The key is sputtering. Let me show you one way to sputter. This is not how a cathode lamp does it, but it would work. You generate one hell of a lot of copper atoms doing it this way in the gaseous state. So let's say we're analyzing copper, so that thing is copper. So my cathode, my anode, and I'm going to generate a hell of a lot of electricity and just sputter this stuff off. I mean, you'd almost have to have a vacuum in here, a really low pressure, so that you can collect, so these, they'd actually appreciate. Because now you have this empty room, stuff is going everywhere, right? But yeah, I'm physically destroying this thing. I'm kicking them off, okay? Now that's not what's making the noise. What's make the noise? A whole other story. What's making the noise? It's lightning. What's lightning? I'm actually tearing the air apart, so that for this charge to get from here to there, I'm actually tearing the air apart because air is an insulator. So the air has to get ripped apart. Charge passes through, but the air slams back down on itself again. So you hear the thunder, or you hear the.
So when you're saying that, so it's not actually like air has the nitrogen off, it's moving them all apart from each other, so it's creating.
Yeah. So you can't now. So this isn't going to work you don't need that much. Plus, it's going to destroy the whole damn lamp. So what they do is they fill this with an inert gas. Now, neon. Does neon is neon polar? No, right? I mean, it's just think of it as a sphere almost of charge. And so yeah, we have plus minus here. Neon doesn't care, doesn't have a charge. If it was polar, it would actually suck up to one. That's the idea. Somehow make neon polar so that if the cathode is super positive, neon has a partial negative charge, it slams into it, kicks those copper atoms out, right? How can that be? How can neon possibly get a charge? No, we're thinking too permanent. This is happening all the time. If you have a sphere of charge like neon, right? I don't know how to draw a sphere. How do you draw a sphere, right? And it collides with another sphere, or it collides with the glass or something like that. Does the electron distribution stay the same? No, it's going to change. It's that van der Waals forces. It's that. Okay, now hang on. So, are you with me so far that the electron distribution will change just for a very short period of time, but it will change? It'll change, right? Well, that instant that it changes, charge, bam, it gets it accelerated. Yeah, I'm sure by the time it finally strikes the cathode, it doesn't have its polarity anymore because it disappears so fast. But the point is, you already got it moving. And you got it moving with a really high rate of speed. We're not after a whole lot of copper to get into the gaseous state. In fact, we don't want very much because our lamp isn't going to last very long if we get a lot. So you don't want a lot. So this thing, it's the same thing how these fluorescent tubes work. It slams in there, do some sputtering. Okay? So then these copper atoms that are excited, they release, and the ones that do release their light, yeah. And then hopefully they'll end back up on the cathode. Okay, so that's the idea of this sputtering. The neon is key. Okay? And so is this voltage difference. Otherwise, you're not going to get the neon to accelerate towards the cathode in the first place. Okay. Why? isn't going up and down. Why are hollow cathode lamps cylindrical?
It gives provide a reflective point for the neon, so once you sight it and it bounces somewhere, you don't want it to just
Well, it's gonna
right back.
the
Bounce somewhere else.
well not maybe, but the light goes everywhere, so you can't really do anything about that. But I guess the guys who made these things found out that these cathodes last a lot longer. Somehow, because it's cylindrical, the copper atoms deposit. That's what I read. I don't really see how it matters. But the cylindrical shape is supposed to help the redeposition of the copper or the metal element of interest back onto the cathode. But I don't. I guess I just don't see it.
Is it just
But
shape and things hitting a cylindrical surface makes it more likely to come back to the center?
I
Since
guess
everything's
it
like
could be.
centered
Yeah, I
around
think of the
this
focal
spot,
point.
I think that's what Brad was saying, that like since it's shaped in that way, the neon gas will, or I don't know, I guess the
Yeah,
copper would redeposit on there.
But I think it's more complicated than that too, because if you do take this out, look at there's one big spot on here, right? So
Burn copper, or in that case, burn sodium and potassium.
so I think I know they put that there for a reason. This spot. So there's more complicated things going on here than just a cylindrical shape, I think. But I could be wrong. But the argument has always been cylindrical shape is for redeposition. But I think it's more complicated than that, but that's their argument. Okay. Man, I lost my mouse doesn't work anymore. There's some interferences. Okay, you can have interferences. That's what this plot was all about. This plot was all about interferences. So there's two types. Spectral interferences, rare though. Because that means that there's something in the flame or something in your sample that absorbs, has the exact same absorption spectrum as sodium does, if you're looking for sodium. These guys are so narrow, that's so rare. Or to have two elements that perfectly lined up and you just happen to pick that wavelength to analyze. So that's pretty rare though. But if it does happen, we use background correction. It's supposed to help, I guess. Chemical interference is much more common. We did a lab where we had to add lanthanum because we have a chemical interferent. So there's some chemical present in the flame that interacts with the metal to change the metal's absorption spectrum. Usually, very often, it's just, dang, we're generating a lot of copper plus 2 ions. Well, you don't want copper plus 2 ions. You want copper atoms. So you might have something like lanthanum that kicks in a whole lot of electrons in the flame. There's just a lot. So it suppresses the formation of copper ions, and you just get the copper atoms. That's very often what's going on. But these are chemical interference. So you add something chemically to help yourself out. Sometimes changing temperature helps because then maybe it won't ionize so easily. Okay, but just throw lanthanum in there, it helps. Calibration curves in AA spectroscopy are usually, yeah, if you follow the cookbook, right? They're just trying to say, in general, you just randomly go put stuff together and try to make a calibration curve. You're not going to get something linear. So you pretty much have to follow the AA cookbook. And then you could say then they are linear, yeah, if you follow the AA cookbook. I would say not linear because the way the question is phrased, right? The goal is to make them linear, so follow the AA cookbook. Now I have one more thing here I just added. Here's a double beam spectrophotometer for the AA. Now for a single absorbance measurement, we need how many measurements? 2 measurements. Okay. The reference and the sample. Right. Okay. Do you recognize them? Oh, they use P and PR. Let's get rid of this.
So PR would be the reference.
Yeah, PR is the reference. And then the transmitted intensity is P. Now, do they have different light paths? Yeah, they do. Which one, only one of them goes through the flame? Which one? The P, the transmitted. They didn't bother having the reference go through the flame. Why? Shouldn't they have? I think what this really brings out is the power of the double beam spectrophotometer. We assume that the light and all these electronics, that they work so awesome that we can use them and they're going to respond exactly the same no matter when you start, whenever you turn things on, or how old they are, or the temperature of the room, humidity. We think things are working great all the time. No. This really points out that you don't need to run. The important part of that reference is to take into account the changes in intensity in the lamp and the changes in detection efficiency, sensitivity. That's the true job of the reference. So, like I said, going back to the UV vis, the best reference to use is nothing, right? Because your goal of the reference is to take into account changes in the intensity in the lamp and changes in intensity in the sensitivity of the detector. Okay, so it must be cheaper for them to do it this way. Otherwise, they'd send them both through the same path, I think. I don't see why they would do it this way. It must be cheaper. Because the flame doesn't matter. The flame's not your issue. It's the change in intensity. And I guess you can kind of really tell with the AA. Because you turn that thing on, and you can actually do see it does get a little brighter over time. Okay. So that's all I have. So happy Valentine's Day.
And was that double beam flame spectrometer added?
I added it this morning.
Oh, okay.
Yeah, so you don't need to draw it or anything. It's just,
Okay. And this is online now.
yeah.
Right,